Bismillahirrahmanirrahim. Hello dear students, hopefully you are fine. I welcome you all in class of Operation Research. We will continue our discussion from maximal flow problem. In the last lecture, we discussed about maximal flow problem about the network model in which only one directional flow is allowed, that is forward flow allowed. For example, in the last lecture, the network model that I shared or discussed, you can notice that from node 1 to node 2 there is a 7 unit flow allowed, but this is a forward flow. In the similar way, you can notice other nodes from node 2 to node 5 there is also only forward flow allowed, that is 5 unit flow. Similar way, from node 2 to node 3 there is 1 unit of flow allowed. So there is no edge which have backward flow. In today's lecture we will discuss a network model which have forward as well as backward flow. Sometimes it is also called the case of bidirectional capacities. So here flow or capacities is a unidirectional or one-way direction. One of the example that I will share here, find the maximal flow in the given network model. Here in this model you can see that at every edge there are the two numbers. One number is after the node 1 and one is before the node. For example, this is node 1 and this is our node 4, and this line that joined this node is called edge or arcs. The number after the node 1 is 10. This shows that there is a 10 unit of flow from node 1 to node 4. And the number before the node 4, that is 0 here, this shows that there is a 0 unit flow from node 4 to node 1. In other words, we can say that the reverse flow is not allowed here. But if you notice on node 4 to node 3, both the numbers at node 4 and node 3 are non-zero. At this edge, this is a 5 unit flow and this is 10 unit flow. So this shows that there is a 10 unit flow allowed from node 3 to node 4, and the backward flow is also allowed from node 4 to node 3, that is 5 units. In the form of loop, this discussion can be elaborated as this is node 4, this is node 3, so there is a 5 unit flow from node 4 to node 3. In the similar way, from node 3 to node 4, this is also 10 unit flow of allowed from node 3 to node 4. So this is the case where the forward flow as well as backward flow allowed at the same times. Whereas in this figure there is a no edge which shows forward as well as backward flow. So if you have such type of network model, then to find the maximal flow by using Ford Fulkerson Algorithm method, the method will be and one of the important thing that because my native language is Urdu, if you find any deficiency in English or you find any grammatically mistake, I apologize for that in advance. So let us start how we will solve this network model by using Ford Fulkerson algorithm method. In the start, we will suppose there is a 0 unit of flow at the sink node. A node is called sink node which have only incoming flow, no outgoing flow, which have only inward edges, no outward edges. So in the figure there is only one of the node which have only incoming flow or inward edges, that is node 5. Because node 5 is attached here with node 3, node 4 and node 2. And from node 4 you can see that there is 20 unit of flow to node 5. Also there is 20 unit flow from node 3 to node 5, and there is 30 unit of flow from node 2 to node 5. So node 5 is sink node, whereas node 4 is neither sink node or node source node, because it has inward edges as well as outward edges. Node 4 is attached here with node 5, node 1 and node 3 at the same time. So from node 1, node 4 has a 10 unit of flow, and at the same time node 4 has 5 unit flow from node 3. Node 4 has a 10 unit of flow from node 3. And the flow that passes through from node 4 to node 5, that is a forward flow, is also here 20 units. So the node 4 has inward flow as well as outward flow. So node 4 cannot be sink or source node. In the similar way, node 1 is here source node. So a source node, a node that have only outward edges or outward flow, but no inward edges or inward flow. So you can see that node 1 has only outward flow. Node 4, node 2 and node 3, 3 nodes are attached here with node 1, and you can see that there is a 10 unit of flow from node 1 to node 4, there is a 30 units of flow from node 1 to node 3, and 20 unit of flow from node 1 to node 2. So there is only a forward flow from node 1, and node 1 does not have inward flow here. So here node 1 is a source node and node 5 is a sink node. So suppose that at the initial stage our node 5 has a 0 unit of flow. Next we proceed as here. We will solve this problem by Ford Fulkerson algorithm method. Ford Fulkerson algorithm. In this method, firstly, for the iteration 1, let us choose an augmenting path. Augmenting path is a path in the residual graph that join node source node to the sink node. So one of the augmenting path that join source node to the sink node is we move from node 1 to node 4 and then from node 4 to node 5. So first of the augmenting path is node 1 to node 4 and node 4 to node 5. This path consists on two edges. One edge is node 1 to node 4 and other edge is node 4 to node 5. These two edges have the capacities. First edge have a non-zero capacity, that is 10 unit, and second edge has a non-zero capacity, that is 20. So after choosing augmenting path, this is our augmenting path. After choosing augmenting path, we find bottleneck capacity. Bottleneck capacity. Bottleneck capacity of this path is the minimum of, this is the minimum of the number. First number is 10 and second number is 20. First number is 10, second is 20. So the bottleneck capacity in this case, this is equal to 10. Next, we find the residual capacity. How we will find here residual capacity when our network model consists on forward as well as backward flow. We subtract bottleneck capacity. We subtract bottleneck capacity that is 10 unit here, that is 10 units here, 10 units here from every capacity next to the node and add this capacity from every number before the node of every edge that is associated with our augmenting path, to find the residual capacity. Further, this bottleneck capacity we add at sync node to find the maximal flow after each iteration. So the resulting residual graph will be so we make this figure again. After first iteration, this is node 4, node 5, node 1, this is node 2, node 3. We join these nodes. Next 4, 3. Okay, now we change the numbers on every edge like this. Here in our first iteration, in our augmenting path, the bottleneck capacity is 10 unit. So we subtract this number 10 from the first number of this path, this edge. That is 10 minus 10, this will become 0 here. And at the same time, we add here that 10 unit to 0, this will become 10 unit. Now this shows that there is a backward flow also from node 1 to node 4 to node 1, that is of 10 unit after first iteration. Similarly, we subtract that bottleneck capacity from the first number, that is 20 here. This will become 20 minus 10, that is equal to 10 here. Similar way here we subtract, add this bottleneck capacity, this will become 10. Now the maximal flow after first iteration will be at the initial stage the flow was 0. Now the 0 plus 10 means the bottleneck capacity. This will become 10 and the remaining figure will be same. This is 30, this is 0, node 1 and 2, this is 20, this is 0, this is 40 and this is 0, this is 10, 5, 30 and this is 0. Okay. After first iteration is complete now, next we move to the second iteration and again we will find an augmenting path. So whether there exists any augmenting path now. Next augmenting path is here, iteration 2. In the second iteration, we can find the next augmenting path by joining node 1 and node 2, that is from node 1 to node 2, node 2 to node 3 and then node 3 to node 5. Now our augmenting path is augmenting path. Consider the augmenting path node 1 to node 2, node 2 to node 3 and node 3 to node 5. Again for this path we will find bottleneck capacity. B and C mean bottleneck capacity, that is the minimum of 20, 40 and here was 20 and this is 0, 20. Now the minimum of these three numbers is 20 here. So the bottleneck capacity at this time is 20. Similarly as in iteration 1, we subtract this bottleneck capacity from the number after to the node and add this bottleneck capacity to the numbers before the nodes. And the remaining procedure will remain same. So the resulting graph, that is the residual graph, will become node 4, node 1, node 2, node 5, this is node 2, this is node 3, 1, 4, 2, 3, 3, 5, 1, 2, this is 3, 4, 2, 5, 1, 3. Last flow was of 10 units. Now we will change the numbers on the edges that are associated with our augmenting path. So the first edge is by node 1 and node 2. This is 20. Subtract this bottleneck capacity from this number. This will become 20 minus 20, that is equal to 0. And add this number 20 to here. This will become 0 plus 20, which is equal to 20. This is equal to 40. 40 minus 20, this will become 20. And here 0 plus 20, this is equal to 20. At node 3, this is 20 here. 1 to 2, 2 to 3, 3 to 5. This is our last edge of our augmenting path. 20 minus 20, this is equal to 0. And here number is 0. 0 plus 20, this is equal to 20 here. Now the maximal flow after the first iteration will become 10 plus 20, this is equal to 30 units. And all the numbers of the remaining figure remain as it is, that is equal to 0, 10, this is 10, and this is also 10, this is 5, and this is 10 unit, this is 30, this is 0, node 1 and node 3, this is 30, and node 3 at this is 0. After second iteration, our flow is 30 units. Next we move to the iteration 3, and again we find an augmenting path if possible. Iteration 3. What will be the iteration 3? Now we find the augmenting path. One of the augmenting path is, if we move from node 1 to node 3 here, the starting capacity at node 1 is 30, that is non-zero. We cannot move from node 1 to node 4 because the starting capacity is 0. 0 means there is a no flow allowed, because there is no flow here. To move from node 1 to node 1 to another node, it is necessary that there should be a non-zero capacity at node 1. So the non-zero capacity here, that is 30. So we can move from node 1 to node 3, and then from node 3 to node 4, and then from node 4 to node 5. Now I am choosing the augmenting path node 1 to node 3, node 3 to node 5, or node 4 to node 5. Again we will find here bottleneck capacity. B dot and C mean bottleneck capacity here. This is minimum of non-zero capacity between node 1 and node 3. This is 30 units. Then from node 3 to node 4. 3 to 4, this is 10 here. Node 0. 0 is the capacity from node 3 to node 1. 10 shows the capacity or the flow from node 3 to node 4. The two capacities between the node 3 and 4 are 10 and 5. Okay. So this is 10 unit, and again from node 4 to node 5 the capacity is 10 unit. So the minimum of these three numbers is 10 unit. As the similar as the previous iterations, we again subtract these bottleneck capacity from the numbers after the nodes and add this bottleneck capacity to the number before the nodes of every edge that are associated with our augmenting path. So the resulting residual graph will be now. We again take the figure 1, 4, 5, node 2, node 3. Okay. So firstly consider the first edge. The first edge is between node 1 and node 3. At the node 1, the capacity is 30 units. So we subtract this number 10 from this number. This will become 30 minus 10, this is equal to 20. And add that bottleneck capacity, that is 10 unit here, to add this number 0. This will become 0 plus 10, 10 units. Then the second edge in our augmenting path is between node 3 and node 4. So at node 3 the capacity is 10 unit. So we subtract the bottleneck capacity from this number. This will become 0, and by adding this number this will become 15. Then we move from node 4 to node 5. Now here the bottleneck capacity, residual capacity will become 0 here, and by adding bottleneck capacity to this number this will become 20. Now after third iteration our maximal flow is, in the last figure the maximal flow is 30. Now our flow is 30 plus 10, this is equal to 40, and the remaining numbers will be as it is: 0, 10, 0, 20, 20, this is 20, 3 to 5, this is 0, and this is 20, and the numbers between the node 2 and 5 are, this is 30, this is 0, 30, 0. Now whether there exists any augmenting path? Yes, there is a one path remain, and at this point you can notice that the backward flow, we will use backward flow here, and this point is different from from my first lecture. Here the augmenting path that I will choose here, node 1 to node 3, there is a here at node 1 there is a non-zero capacity that is 10 unit here. So I will move from node 1 to node 3, then I can move backward from node 3 to node 2. Node 1 to node 3, then from node 3 to node 2, because at this stage you can notice that there is a 20 unit of flow at node 3, whereas at the initial figure you can check that the flow at node 3 was 0 here. So at the initial stage we cannot choose this path, node 1 to node 3, node 3 to node 2. But now situation is that we can move from node 3 to node 2. This is the difference of this lecture from the previous lecture. Here we can use backward flow as well as forward flow. I hope this point is clear now. In last iteration, next in the last iteration, that is the iteration 4. Iteration 4. Our augmenting path is now node 1 to node 3, node 3 to node 2, and then from node 2 to node 5. For this path we find bottleneck capacity capacity for these two nodes 1 and 3 is 20 here. Then from 3 to 2 again the capacity will be used, that is 20 here, and then again from node 2 to node 5 the capacity is 30 here. The starting capacity for node 2 is 30, node 20. Actually this 20 unit for the edge 2 and 3. So when we use edge 2 and 5, the starting capacity from node 2 is 30. So this is 30. So the minimum of this number is 20. So the bottleneck capacity now is 20 unit. So the last figure here, Okay. Node 1, node 4, node 5, node 2, node 3, now we change the numbers of our edges that are associated with our augmenting bar. The first edge is node 1 and node 3. First edge node 1 and node 3. This is 20 units. So by subtracting this number 20 from this number, this will become 0. And by adding this 20 to this number 10, this will become 30 here. Again subtracting this bottleneck capacity 20 unit from this number 20, 20 minus 20, that is 0. And adding at this position, this will become 40. Then the last edge is between node 2 and node 5. Node 2, at node 2, this is 30. So by subtracting this bottleneck capacity from this number, this will become 10 units. And by adding this 20 at this number, this will become 20 units of flow. The remaining numbers, we write it as it is. This is 0, this is 10, this is 0, this is 20, this is 20 now, this is 0, this is 0, this is 15 units, and this is 0. Okay. And this is 20 here. Okay. Now there is, whether there exists any more augmenting path possible? No. Because you can notice that at the node 1, all the numbers become 0 here. Node 1 is connected here with node 4, but the initial capacity or initial flow at this number, that is the forward flow, is 0 here. Similarly here 0, here also 0. So this gives us guarantee that the now flow is not possible, or there will be no more augmenting path possible. So the last figure shows our augmenting our optimal flow, and our optimal flow will be, in the last figure the flow was 40 units, and now flow is 40 plus 20, that is equal to 60. So this network model has a 60 units of flow by using Ford Fulkerson algorithm method. I hope that this lecture will be helpful for you. Inshallah, in the next lecture we will discuss a new topic. Okay, take care. Allah Hafiz.